So, in the last lecture we discussed the idea behind polyphase decomposition. We also looked into noble identities and interconnecting systems. So, now we have a bunch of identities and useful tools, and using these can we develop efficient structures towards decimation filters, that is you have filtering followed by decimation, or for interpolation filters, that is you upsample then you filter, or by for doing an M by L conversion, right, and how do we realize efficient architectures for sampling rate conversion. So, this is the idea, but two important things you have to consider. So, when you are downsampling you are throwing away samples. So, therefore, is there a way in which you can efficiently make use of the computation, and in the case of interpolation you are upsampling first, that means you are inserting zeros and then filtering. So, that means you are doing a lot of filtering of these zeros. So, you are still wasting computation. So, is there a way to overcome these limitations through efficient design, and we will see how polyphase filtering and the use of noble identities and interconnecting systems and all these ideas that we discussed in the last lecture will be useful towards this purpose. So, let us consider the signal x of n. Now, we are doing filtering first, followed by decimation. So, let us say we are filtering through some h of z, and then we are say downsampling by 2, right. Let us say m equals 2 downsampling. We will decompose this filter h of z using polyphase, type 1 polyphase. So, let us do a type 1 polyphase decomposition. For h of z. So, we get this in this form. So, basically we have x of n we have a filter which is E naught z square. There is a delay element here. We have E1 of z square, and this signal we are downsampling by 2, right. This is the normal architecture. I mean, at least we have done one important step of simplification, that is we have decomposed the filter into a type 1 polyphase decomposition. Now, this structure is still not giving insights to us, because now we are computing something through this equivalent polyphase representation, but we are still throwing away some samples, right. So, let us see if we can bring this downsampler into each of the branches here, right. So, this is equivalent to the following structure. So, we have x of n now I have E naught of z square downsampler, a delay element, E1 of z square. Basically I am pushing the downsampler into each of the two branches. So this is my equivalent form. Not much insight, but I think we would be seeing something interesting if we could swap the downsampler and the filter in each of the parallel paths using Nobel identities. Okay. So we simplify this. As follows, we get x of n we downsample this first. This is followed by some filter of lower order, which is E0 z, delay, downsampler, followed by some filter which is E1, and now we have the output, and I call this structure B. This is post application of Nobel identities. Now in the structure A, because of downsampling, we consider only even numbered samples, right, because we are throwing away the odd samples in the process of the downsampling. Now, which means during odd instants of time, the unit is just resting, which is basically inefficient resource utilization, because filtering and these operations can be costly, right. So now we consider structure B, right, which is this structure. Suppose N0 and N1 are the orders of the filters E0 of z and E1 of z, such that n plus 1 is N0 plus N1 plus 2. Let us say this equation holds, right. That means we have lower order filters for E0 and E1, and the overall filter order is let us assume this is n, right, having n plus 1 coefficients. Now the multipliers and adders in each of EL of Z, so in this case L equals 0 and 1, have 2 units of time for doing their job, and they are continuously operative, that is, there is no resting time, which is important. In the first case there was resting time because you were just throwing away the samples, you were doing some computation, but you were throwing away the samples. In this case you basically have 2 units of time for doing your job and you are continuously operative, there is no resting time. So therefore this is definitely an efficient architecture for realization, right. You are cutting down the filter order in the first cut, that means your number of multiplications and additions would be lower on a per branch basis, and then you are continuously operative because you are not wasting any time here, because you are streaming the odd samples here and you are just basically none of the unit is not resting, right. And if you think about an M phase down sampler, you can imagine your efficiency is M fold, roughly M fold. Okay. So now having seen the advantages of polyphase decomposition and Nobel identities to efficient decimation filter design, let us look into the aspect of interpolation filters. So we have a signal which is discrete time signal here, and we upsample this by a factor L, and then we filter this through some filter H of Z, right, and we have this output. Now clearly a direct implementation of a filter post upsampling is inefficient because at least, say suppose L equals 2, right, at least 50% of the time, this is for L equals 2, we are filtering zeros. The rest of the time you may have some zeros, but at least 50% of the time, since you have inserted zeros 50% of the time, so you are basically filtering the zeros through this filter. So this is inefficient, and those multipliers not resting must complete the job in half the time because output of the delay elements will change with time, right. If you think about any filter, basically you have delay elements, you have some scalars basically to scale the magnitude at the output of every tab delay line. So if you look at a direct form implementation, just brute force way, you are really not efficient, because half the time you are just filtering out the zeros and those multipliers that are not resting, right. So they must complete the job in half the time for L equals to 2. So now fortunately we can think about an efficient implementation for this, and that is through type 2 decomposition, which is type 2 polyphase decomposition of the filter, and then application of Nobel identities. So we will see how this works. So using type 2 polyphase decomposition, so we can write h of z as sum r1 z square plus delay times r naught z square. I mean, we are using the permuted version, right. We discussed in the last lecture about an exercise problem which was linking the type 1 polyphase decomposition to the type 2 polyphase decomposition. So we will basically invoke type 2 polyphase decomposition for the interpolation filters. Now each of these filters RL of z, L equals 0 1, are operating at the input rate and no multiplier is resting. I mean, there is no idle multiplier. So what we do is we have x of n, we feed this through this filter R naught of z. This is post application of the Nobel identities. So you can see the swap between the upsampler and the filter, and also carefully observe the delay element that is appearing at the output here. So this is R1, this is also upsampled, and this is our efficient structure. Okay. So what we did is just at the input side, I mean just we did, so if you just recall here, so we had an upsampling by 2 followed by filtering, right, and the filter we do a polyphase decomposition as follows. So it is going to upsampling followed by filtering through polyphase, and then what we do is basically group the structure very carefully like what we did in the decimation filters. So we swap using Nobel identities, the upsampler and the reduced order filter, and we have an efficient architecture for doing interpolation. Now you can imagine the scaling in terms of efficiency for L-fold expansion, right. If you did an L-fold expansion, you are inserting L minus 1 zeros into the signal, right, and therefore a lot of filtering is happening through these zeros. So therefore we want to cut down, you are drastically wasting your compute power and efficiency and the delays, I mean resting of the filters. So therefore using type 2 polyphase decomposition we can realize an efficient architecture for interpolation filters. So we will also study some important properties with linear phase FIR decimation filters. Now if I give you a general FIR filter, possibly which is symmetric, right, do we see any structure in the polyphase components, right? This is another thing which we have to sort of investigate. So one is we have an arbitrary filter, right. Now we have any h of z, but when you do filter design, sometimes you can exploit properties in the construction of the filter itself, right. You might want to bring in some symmetry in the filters for efficient computations, and if you bring in some symmetry, then what is the impact on polyphase filters, and then on top of it, coupled with this efficient architecture, for realization you are much better in terms of your realization. Okay. So let us look into the next aspect, which is linear phase FIR decimation filters. So let us suppose we have a filter with impulse response small h of n such that h of n is h of n minus capital N minus small n. I mean, this is symmetric, right, this is symmetric. Let us investigate how symmetry in h of n reflects into the polyphase components. Now for any n, capital N, there are only two possibilities. N could be odd, n could be even, right. So let us just take some examples here, sort of get a feel for what is happening. Let us choose capital N to be equal to 4. So that means I have 5 coefficients, right, n plus 1 coefficients. So let us assume that h of z is of the form 1 plus 2 z power minus 1 plus 4 z power minus 2 plus 2 z power minus 3 plus z power minus 4. So now we are familiar. Basically, if you want E naught, we take 1, 4 z power minus 2, then we choose this as one part, and then we could choose this and this as our second part, right, for L equals 2 polyphase. Let us take two phase decomposition. So M here, M equals 2 in this case. Now I have E naught of z is 1 plus 4 z power minus 1 plus z power minus 2. Recall 1 plus 4 z power minus 2 plus z power minus 4 is E naught of z square. If you want to get the reduced order, I mean, you just look at E naught of z, which is going to be this, and similarly you have E1 of z, which is 2 plus 2 z power minus 1. And if you observe this carefully, right, basically these filters are symmetric, right. So, each of the polyphase component filters are symmetric. And one can think about how you can exploit symmetry to do your filtering of operations efficiently, right. Let us look at the other case, which is the odd case. Suppose n equals say 5. Let us consider h of z to be 1 plus 2z power minus 1 plus 4z power minus 2 plus 4z power minus 3 plus 2z power minus 4 plus z power minus 5. I mean, observe the symmetricity, because we have started with the constraint that h of z should have a symmetric impulse response, right. Now, when we do the polyphase decomposition, we get, just to recall, you take this and then you take this, and for the other case you take this, you take this, you take this. Okay. Now, E naught of z is basically 1 plus 4 z power minus 1 plus 2 z power minus 2, and E1 of z is basically 2 plus 4 z power minus 1 plus z power minus 2. Now, we observe E naught and E1. Unlike the even case, these are not symmetric, but E naught and E1 are mirrors. Of each other. You look at this 1, 4, 2, and you see the mirror of this, which is 2, 4, 1. So, there are some nice structures which are hidden into these polyphase filters, and we should be clever to exploit these structures to basically save our multiplications using some of these components. So, I sort of at this point would give you an exercise to ponder upon. Devise an efficient architecture to exploit the mirror slash symmetric properties of polyphase components in decimation and interpolation filters. Okay. So, we looked at decimation filters, we looked at interpolation filters, we saw how we can use polyphase decomposition and Nobel identities for efficient realization. Then if the original filter itself, of course that did not assume what the structure of the original filter has to be. But if we assume that we start with an FIR filter with symmetric impulse response, right, how can we, what can we say about the properties of the polyphase components? And now we know that they could be mirrors or they could be symmetric filters, that is the polyphase filters could be mirrors when n equals odd, and it could be symmetric when n equals even. Now considering these other additional properties, can we build and devise an efficient architecture to exploit these properties?